Welcome. Myself and Max Sorensen will be summarizing the unit of electrostatics. Now, the first thing to understand is charge. You might ask, what is charge? Well, you'll need a basic understanding of it to understand how objects can interact electromagnetically with each other. The charge of an object is caused by the ratio of protons to electrons. Electrons have a negative charge, whereas protons have a positive charge. A negatively charged object has more electrons, whereas a positively charged object will have less electrons. Because obviously, protons can't move around like electrons can. Now, the electrons, and therefore the excess charge, is located on the outside surface of the object. As you likely know, like charges repel, whereas opposite charges attract. There are a couple other fundamentals needed to understand charge as well. First, matter is neutral when it has equal amounts of positive and negative charge. Similarly to energy, charge is conserved and cannot be created or destroyed. Finally, when calculating charge, the smallest amount of charge is 1.6 times 10 to the negative 19th coulombs, because that is the charge of an electron or proton. Therefore, any charge must be divisible by this number. Welcome to the second section of our summary of electromagnetics. This will be polarization. But first, we have to explain some more basics. So, to make a charged object neutral, you have to ground it, which means touching it to either the ground or conductive material that is also touching the ground. A conductive material, or a conductor, is something that conducts charge well, or in other words, electrons. Electrons can pass more easily through it. Whereas the opposite of this is an insulator. An insulator does not let electrons pass very easily through it. So, to polarize an object, you're going to need an insulator under. Polarization is a state in which an object that is neutrally charged can be affected by a charged object. So to get this, for instance, if we had a neutrally charged object and brought a negatively charged magnet close to it, but not touching it, then the electrons in the object would gather farthest from the side of the magnet, because they're being pushed by its negative charge. The polarized object can now be charged if you touch a conductive material to the polarized object. Then electrons flow away from the negative magnet through the conductor and leave the object temporarily positively charged. When you take away the material, the previously neutral object will now be permanently positively charged, until it is grounded again and its charge leaves it. Welcome to the third section of our summary of electromagnetics. This will be Coulomb's law. Coulomb's law gives us the equation to find the electric force between two charged objects. So, the equation for Coulomb's law has K times the absolute value of Q1 times the absolute value of Q2, all over R squared, which is equal to the force between the two charged objects. The product of the charge is divided by R because the force between charged objects decreases over distance, similarly to how the force of gravity works. The absolute value signs are there simply to make the calculations easier. However, make sure to remember to check whether the force is repulsive or attractive. K is the electrostatic constant, which has a value of 8.99 times 10 to the negative 9th newtons times meters squared over coulomb squared. When doing problems with more than two charged objects, you must take into account the fact that the forces are vectors, and take the sum of these factors from all charged objects to find the net force. Now, I'll be handing you off to Max for the other half of this review.
Hello, and welcome to the second part of our lesson, electric field. While we can use Coulomb's law to find the force between two objects, we know that these objects will provide a force all around them, not just between that interaction. So we can't always use Coulomb's law to think of the electrostatic force a charge creates. So how does this force travel from one charge to another? We can model this transfer through an electric field model. By this model, we say that a charge alters the space around it, creating an electric field E, and another charge, when placed in the field, will experience a force F, exerted by that field. We show the electric field with vectors coming to or away from the charge. Positive charges with vectors going away, and negative charges with vectors going towards the charge. The direction of the arrows is based on the direction a small positive charge would travel as a result of the field. This positive small charge is called a point charge. The way we calculate an electric field is with the formula E equals kq over r squared, with r being the distance away from the charge that is exerting the field and q being its charge. Or you can calculate it with E equals F over Q, with F being the force caused by the field on another object and Q being the charge of the object experiencing the force. When dealing with more than one charge, the vectors will act differently depending on the charge of the object. For example, two objects of the same charge will have their arrows curving away from each other. Objects of different charges will have the arrows coming from positive to negative. There are 4 things to remember when drawing out your field model. Electric fields are tangent to the field at any point, so the vectors will coming straight out of the charge. 2. The amount of lines coming to or from a charge is proportional to the force caused by the electric field. So, a charge with an electric field of 2E will have double the lines of a charge with just a charge of E. And we always go from positive to negative. Positive lines theoretically go on forever, seeking out a negative charge. And lines shall never cross. There's another concept that goes along with the electric field, the uniform electric field. It is similar to the normal electric field, but all the field lines are in the same direction. As seen in this diagram, a uniform electric field exists between 2 parallel plates, one positively charged and one negatively charged. Just as in a normal field and a uniform electric field, other charged objects, such as point charges, will be manipulated by the electric force caused by the electric field. For instance, in this diagram, we can see a negative charge be affected by 2 uniform electric fields. The first is shot out of the first electric field because it is being repelled by the negative plate. Then it is being forced upwards at an angle by the electric force of another electric field. Because the fields are uniform, the distance away from the center of the field does not matter as much as a normal electric field. What matters more is the time spent within that electric field, so the electric field can act on the charged object for longer. Okay, so to show your understanding of this lesson, let's do a little lab. You need a full balloon, hair or shirt, and a can. The balloon will be the object you charge, hair or shirt, the way you charge it, and the can will just be a neutral object. So you'll charge up the balloon on your hair or shirt by rubbing it, and then you'll place the can on the side and put the balloon close to it but not touching. This will make the can polarized and be attracted to the balloon. Observe how strongly it is attracted and then repeat this process multiple times. Each time, charging the balloon more and more on your shirt. This will hopefully make more electrons be attached to the balloon, and it will make the balloon a more attractive force for the can. This will hopefully show you how more electrons and more charge makes the electric force stronger between objects.
The end.